All right, so. Guessing there's no. Oh, yes, you got a question?
Yeah, 3.9, number 21.
To operate. It's almost. It'd just be a whole hour of me just fumbling with the camera. Okay. So this one says the altitude of a triangle what do you want to call this? First off, is that cool? Altitude is just another name for the what of the triangle?
Height.
Height. All right, let's call this sucker H. Yeah. Altitude of a triangle is increasing at a rate of 1 centimeter per minute. So what equals 1? DHDT, right? So we gave that a variable. You didn't have to call it H. You could have called it little a, but there's already an A for area, so might as well call it H. Yeah. So the change in height over time is 1 centimeter. I'm going to put this in per minute. Our little triangle is growing up. While the area is increasing at a rate of 2 square centimeters per minute. So what would the symbols be here?
DAD.
Yeah, the area over time rate change is 2 square centimeters a minute. I like it. So again, it's basically your first step is draw a picture if it's applicable. Whatever they give you, identify variables and identify symbols, right? The notation to use. At what rate is the base of the triangle changing? So what do you want to call the base? Holy shit. At what rate is the base of the triangle changing? So what is it they're asking me for in symbols?
dV over dt.
dV dt. dV dt. When the altitude is, okay, here comes the snapshot. When the altitude is 10 centimeters, so what would that be? H equals 10. And the area is 100 square centimeters. So that's the snapshot. This is the stuff you do not plug in at first. This is stuff you plug in after you've done derivatives. Okay, so the few homeworks I've gotten so far looked at from this section, some of you guys are just putting stuff in too early, right? That's throwing you off. If you put constants in too early and then take derivatives, that piece goes to 0, you lose all the information. Derivatives are supposed to be generally true, and then you can plug in specific times, right? Okay. All right, what am I missing that I need to work with? I've identified everything they've told me. What formula do I need that would involve all this stuff?
Area of the triangle.
Area. What's the area of this triangle?
1/2 base height.
Yeah. Right, good old 1/2 base height. Base height. Half height base, half height base. Right, sorry. And then, okay, all right. Everything I just did, easy shit. They told me this. I can make whatever variables I want to, and then when they give me a rate, I identify that rate with a symbol. So, right? So then, when I do derivatives to this, I can throw shit into the right place. Does that make sense? I mean, now, this is a relatively easy problem. I'm not trying to make you feel bad for asking me this question, but some other problems get a little more complicated, but they're all basically the same. Identify the variables, identify the symbols for what they tell me, and then what is the overarching equation. So this relates base, height, and area. I need something that relates rates have changed, so of course, what do I do?
Derivative.
Take the derivative. Now this is where things get interesting. Notice they didn't tell me like the base is twice the height or anything like that, right? So what's going to happen when I take this derivative? I'll do this side. I did a whole side. Okay. It's always funny, Jeff. How do I take the derivative of this side with respect to time? What's going to happen?
dB dt.
What rule do I have to use?
Oh,
Product rule, right? Isn't base a function of time? Isn't height changing over time as a function of time? So this is a product of two functions, yes? So now, a lot of problems, they tell me something, they ask me something. They actually give me a relationship between B and H so I can eliminate one of the variables so I don't have to worry about product rule or whatever. Yes? This one, they didn't. Too bad, so I've got to use product rule. That's kind of like why we want to eliminate a variable if we can, because then the derivative is a little bit easier to work with. But here, we can't, so too bad for us. So what would this be? 1/2. Right? Product rule. So we're going to do this guy first, right? What's his derivative? No.
dB dt.
dB dt. Right? You actually know it's got to show up, yes. Derivative of that with respect to time is dB dt times h plus, now it's h's turn. And do you see how this tells you what to expect? Do I see this? Yes. Do I see this? Yeah. Do I see it? Yeah. Right? That kind of makes sense now. The most important thing to see is this, because that's what the freaking question is. So if I don't see this, I can't answer the question. I've done something wrong. Okay. And all right, that's all I'm going to do, because now you just plug shit in. Yeah. Now I want you to realize something. They tell me what H is. They tell me what the area is. Is there an A? Be really careful. That's not an A. That's a dAdt. Is there an A in this equation? No. So watch this. This is what you got to ask yourself. Do I know dAdt? No, that's what I'm asked for. Do I know H at the moment? Yes, right? Do I know dH dt?
Yeah.
Yes. Do I know dAdt?
Yeah.
Yes. Can I solve for this then, or am I missing something still? I'm missing frickin' B, yes? Do I know A at the snapshot? Yes. Do I know H at the snapshot? Yes. Can you solve for B? But I mean, do you see the motivation? At this point, I'm like, that's what I want to solve for. I better know everything else. And if I don't, I got to take a second and figure it out. Does that? I really want this to make sense. If you want to solve for this, you better frickin' know everything else. Yes? Doesn't that make sense? And if you don't, you just say, oh shit, okay. Did they give me enough information to figure out the last thing I need? Yes. So if you came in this class expecting to get, here's the equation, here's what everything is, plug it. No. Right? You're gonna have to stop and think, okay, I need this, here's what they told me, can I get what I need? Is that cool? I mean, it better be cool, because it's almost done. So that one, I like that problem. It was difficult because it was different, because they didn't let you kill a letter. You get kind of used to that. But they gave you enough information, you didn't need to kill a letter. Yeah. Yes?
Number 18 on that
18?
Yeah.
Oh yeah, this is a good one. This is a classic related rates problem. Good Lord, man. It's not me, the room is. I'm not drunk, the room is. Okay. Yeah, they love spotlights on stuff. So a spotlight on the ground shines on a wall 12 meters away. There's a spotlight shining on this wall. Okay, so that's your beginning rough sketch, right? if a man 2 meters tall walks from the spotlight toward the building, okay, where am I going to put the man?
At the little.
At the bottom left corner where the spotlight is, because he has to walk in the spotlight of the building.
Yeah, but I'm going to let him be somewhere. I don't have to put him right here. I'm going to let him be in here somewhere.
Yeah.
Right. So he's 2 meters tall. And what I'm really, now here's the thing. Let me kind of improve my picture. Well, I basically got this picture well enough. Because what I'm going to be curious about is the shadow he casts on the wall. Now, from experience, if I have a wall and I have a light behind me, what happens to my shadow as I walk closer to the wall?
It's smaller.
It gets smaller, right? And so if I walk towards the spotlight and I'm blocking more of the light, my shadow's going to get huge, yes? When you're a little kid, it's kind of fun to do, right? So right here, the way I've got this set up, let me do this a little better. The way I've got this set up, this would be the shadow here, yes? And as he walks closer, this would actually get lower because I'm going to go over right to his head, and then the shadow gets smaller the closer he gets to the wall. So physically, that makes sense. And do you have to do what I just did? No. But it's always good to just stop and say, does this problem make physical sense? Okay. Because if it didn't, that would be a problem. Where'd it go? There it is. Toward the building at a speed of 1.6 meters per second. How fast does the length of a shadow on the building decrease? Oh yeah, this is beautiful. All right. So what are all the variables I need? First off, is the shadow important? The length of the shadow. Yes, that's a huge part. And doesn't that shadow length change as he's walking, right? So what do you want to call that in general?
Yes.
Knowing me, let's choose something other than S.
Y.
Because my S's look like 5s, right? So yeah, you can call it Y if you want to. Or you can call it S if you make better S's than me. So again, the specific problem doesn't matter. What matters is, what is it about the problem that's making me do what I just did? Right now I'm at the stage of identifying the variables, right? What other variable is important? What other piece of this is important? Yes! This distance here. Let me do this a little bit better. So this is 12 meters. This, why is this distance important?
Depending on how far he gets the shadow.
And another thing is, what's one of the rates they give me? Isn't it how fast he's walking?
Yeah.
How fast he's walking, doesn't that control this? Okay, so what do you want to call this?
X.
X. And out of curiosity, what would this be?
That's gonna be 4, right?
Don't say H, don't say Z, don't say any of that. It's, sorry.
Oh, never mind.
Not yet. In general, what is that?
12 minus.
Yes, if that's X, and that's 12, this has got to be the rest, right? This has got to be 12 minus X, yes? Right, isn't that the definition of subtraction? Both things 12, that much is X, what's left for him? 12 minus X. You have to stay on top of yourself. Don't put any snapshot information in yet, right? Because otherwise, it'll look like a constant. But isn't all of this shit changing over time? So you don't put a number in there yet, right? Now, real quick, just let you, this section is not easy. It isn't. I don't want me to come off sounding to you like it's easy. It's not impossible either. What's important is, what are the steps? What are the things about the problem that tells me what to do, right? I definitely draw a picture. Most of the problems involve a picture, right? What do I do next? Identify variables, right? Now that I've identified variables in the problem, what do they tell me? What other information do they give me? Where are you at? Here it is. At a speed, he's walking from the spotlight toward the building at a speed of 1.6 meters per second. So how can I identify that?
dx over dt.
Yeah, dx dt. And real quick, one little tiny thing here. Is this getting bigger or smaller over time?
Smaller.
Shouldn't that be negative then? Isn't that getting smaller over time? Yes. Now that's a little tricky. That's okay if you missed that. What else did they tell us? How fast is the length of a shadow on the building decreasing? Okay. So what's the symbol for what they're asking? Do you want, because I've identified the shadow as Y. They want to know how quickly the shadow length is changing over time. So identify in symbols what they tell you. Identify in symbols what they ask you. So then you know when you set up your equation that you have what you need in it. Right? Now what about the snapshot? What's the information from the snapshot? What's the only, at a time when what? When he is?
That's like 4 feet away. 4 meters or 4 centimeters.
Yeah, when he's 4 meters from the wall, right? From the building, they said, but from the wall. So what would be 4?
X.
X. That's the distance from the building, yeah. Freaky shit. Now what? Now what do you do? How many right triangles have I created up there? 2, right? There's this one. And where's the other one?
Small one.
Right. What's special about those triangles? What relationship do they have?
Yeah.
They're similar triangles because they have the same angles, right? Meaning their side lengths are proportional, yes. So what's one proportion I can set up? So, I mean, there's several different ways you can do this. I kind of normally do like, so one example would be small side to big side equals small side to big side. So what would go here? I don't know if do you guys remember this, similar triangles? This one has to be proportional to this one. Isn't this big triangle some multiple of this small triangle? So whatever I multiply this by to get this, I must have multiplied this by to get this. So what goes here? What's a small x side? What's this? 12 minus x, right? And what's this? What the shit? And do you see how that connects? Now, do you want to do derivatives on this the way it is? Wouldn't you much rather simplify, like I keep telling you? Couldn't you solve this for y, for example? And then asking for dy dt? Do you see how that kind of leads you in the right direction? Maybe? Okay. That's all I'm going to do. Keep going from there. Anything else? Yeah, this is good. Thank you. Because if I don't get many questions from this section, I'm like, people forgot it, or they're just on purpose or accidentally forgot it. I don't know. We'll see. Yes?
44.
Or the Lighthouse? Is this the one with a sweeping? Yeah. Yeah. You got a lighthouse. So I'm gonna, all right. So you got a lighthouse on a small island 3 kilometers away from the nearest point on a straight shoreline, and its light makes 4 revolutions per minute. Right. How do you want to draw that?
Circle.
So think about this. Do you want to draw it from the side where you have the lighthouse like this? Do you want to draw it from above? Do you want to draw it from under the water? Do you see what I'm saying?
Yeah.
What do you think?
From above, right?
Yeah, why does it make sense to draw it from above? Because the sweep is a circle. I can see it from above, yes? So here's my little island. Here's my little lighthouse. Here's the coast. Wow! We're gonna pretend like it's just straight. It says straight shoreline. This is one of those places where they just man-made beach here, right? Blah blah blah. It's 3 kilometers away from the nearest point P. Let me stop for a minute. So I mean that, if you have trouble with what I just did, obviously you're never going to be able to do this, right? Most problems involve a picture, and the better your picture is not pretty. I mean, look at my lighthouse. It's a freaking circle. Better in terms of capturing what this is saying, right? Let's see. Its light makes 4 revolutions per minute. We'll worry about that in a minute. How fast is the beam of light moving along the shoreline when it is 1 kilometer from P? Okay. So the light is sweeping, so it's sort of like moving along the shoreline, correct? So at some point, at some arbitrary point, it's pointed at a place on the shoreline. Or, I mean, it could be pointed away, but that would make no sense, because it's all about when it's on the shoreline, correct? So let's just pick, I don't know. You can pick any point on the shore.
Let's see.
Spell that one.
All right, so let's pick here. So right at this, so that, it could have been there, it really could have been over here, but it doesn't make sense, but anytime on its rotation, right? So, let me ask you this. How do I say this? The 4 revolutions per minute, what is that related to? If I, can you draw, the question says, how quickly is the light moving along the shoreline, right? In fact, how exactly did they say it? Well, that's exactly how they said it. How fast is the beam of light moving along the shoreline, correct? So what's another variable that I need to set up?
Time?
Data.
Yeah, you could use theta, right? So here's theta. Because
Distance to the hypotenuse.
what did it say again? Where'd it go? 4 revolutions per minute. What does that relate to? What's a revolution? What does that relate to?
So,
The angle, right? 1 full revolution would be all the way around. So if you, let's see if I can.
send it. Theta, DC.
Say again.
Would it be d theta DC or no?
Yeah, basically, but you can make this better. Let me see if you guys are cool with this. What would 1 revolution around a circle be? Revolutions are not really a preferred. What's the preferred angle measurement?
Radians.
Radians. Why are radians better than degrees? Does anyone know? Radians are definitely better than degrees. Does anyone know why?
They're better, you have better numbers?
They're exact.
Which is built different.
What are radians based on?
Pi?
Why do we call them radians? Do you guys, did we not talk about this? I thought we talked about this.
You take the radius.
If I take the radius and I bend it and I put it here, so this is the radius and I bent it, right? This angle would be 1 radian because 1 radius fits here. Isn't that insane? So that's why we call it a frickin' radian, because it's how many radiuses, radii, fit. And what's beautiful is if I make the circle bigger, the angle's the same. I curve this, there it is. It comes to exactly the same place. So it's an actual physical measurement. Degrees are shit we make up. We just made that shit up. We could have made it 400 degrees. Of course we could. Instead of cutting it into 360 pieces, we could have cut it into 400. We could have cut it into 3 pieces. Do you guys understand that, what I'm saying? So that is no choice. It's based on the radius of the circle. It's not made up. It's physical. Whereas degrees are just, they're not physical. No. I don't know if you guys knew that. Did anyone know that stuff? No? Isn't that cool? I mean, it explains why the shit we call it a radian, because it's based on the freaking radius. All right, I'll stop. So, what's one revolution around? How many radians? How many radians? 2 pi. So how can I write this as 8 pi radians per minute? Yes?
Good, yeah.
4 revolutions would be 8 pi radians. Yes? Okay. I think that's all I'm going to do. I'm going to stop there because I've been doing too much of the other problems. So that kind of gets everybody started, right? Okay. I like this problem. So I don't want to do too much of it for you. Now, one little piece I'll give you a clue on. The snapshot is what? So I will say one more thing. What's the snapshot information in this problem?
When it's 1 kilometer.
When it's 1 kilometer away. So that's when this distance is 1. So don't I need a variable for this distance? Okay, that's all I'll say. That's all I'll say. Okay. Anything? Those are good. Those are really good. Those are the problems. Like I said, if I don't have anybody asking about those kind of problems, I'm worried that nobody's doing it. All right. So let's get back into. Oh shit! Did you not turn on? So I'm going to show you a nice Desmos demonstration of Newton's method that will obviously beat whatever I try to draw last time. I am the furthest thing from an artist that has ever existed. Well, no. One of my math teachers was the furthest thing from an artist. I'm the second furthest thing. And by the way, all right, real quick. If you just Google, for example, Google Newton's method Desmos. That's I didn't create what I'm about to show you. Screw that. Somebody else created it. Why would I create it? I made it better, but do you understand what I'm saying? Desmos is stupid powerful. There's all kinds of things people have pre-programmed in that you have access to. So you can type in almost anything we've done and put Desmos at the end, and there's probably a demonstration pre-built for you to watch if you want. If you want to. You guys see that okay? Yes? No? Okay. So here's the thing. See up here? There's the function we're working with, right? And here, let me see. I'm going to turn on flames just so I can see that. Yeah. So, let's say let's actually do this. Let's say I'm trying to get that root. Is this a good first guess?
No.
I'll be all right. Okay. Why is it not a good first guess?
It's so far away.
It is far away, yeah. In fact, let me get a little closer. Let me get more than halfway. Right? Do you guys see how this would be halfway right here? You guys kind of agree with me?
Yeah.
But look what happens to get here. You can do it, Jeff. There, okay. That's more than halfway towards this root, yes? Right? It's more than halfway to it. But is that a good guess? No. So here's the idea. Here's my x1. Yes, this is my first guess. And we'll talk a little bit in a minute about how to get a decent first guess. So then what's the process of Newton's method? Find a tangent line at that point, and then where's my second guess?
Right.
It's off the screen, right? So let me do this. My second guess is right there. And that is bad. And if all right, so this is just a really quick example about how your first guess, even if you're like 0 to 2 halfway, so I'll go a little bit closer, you're still not going to get that answer, are you? So your first guess has to be really pretty decent, right? So let's improve our first guess a bit. There. Now here's one thing I want you to realize. Is our second guess actually closer than our first guess was?
No.
No, it's a little bit further away, right? But what would I then do? So here's my first guess. To get a second guess from that, I'm going to repeat the process. I'm going to find the tangent line, right? I'm going to find the tangent line. Wow! And then where it hits the x-axis, it's going to be around right there. Can you guys see that? So if I find the tangent line to the curve, I think it's going to be around here. Let's see. Hey, look at that shit. All right. So again, I really want this to make visual sense. I have a root I want. Get a decent first guess. Get the tangent line, and then its intercept is my second guess. Then I just do the process again as if this was my first guess. I find its tangent line, that's in green. I find its x-intercept. That's my third guess now, right? Then what do I do? Do it freaking again. Get the tangent line. You see how that's going to just get closer? All right. So if I do it again. Pop. Look at that. Look at that. Look how close we are. And if I do it again, that looks perfect, right? Let's see. All right, there we go. That's pretty good, man. That's especially for government.
There,
That's
it's
good.
like with hundreds slice.
Yeah. So what do we get there? We actually get 2.0002. And the actual answer is this. Wait a minute. All right, I forgot to change that function. Dadgummit, Jeff. Get out of here. No, I'm sorry. What I want is, see if you can handle this. That's the problem with doing things on the fly. Can you do that? No, you can't solve it. Screw it! Whatever the real root is, okay, that's pretty damn close. So the real root is actually 2. And we got 2.0002. That's pretty damn good. Now if I did it again, it would get even closer, right? Okay, now, that's the visual of the process. That is actually what's happening. And you can see, for example, if I go back and make what seems like a decent first guess. And again, the part we normally don't do is we normally don't actually plot this function. So if I take a guess like, right, maybe there, I can't get it perfect. No, definitely. About right there, it's almost horizontal, right? I wonder if it'll, no, look at that, it's good work. Yeah, that's having issues. I like it. You guys kind of see what I'm saying? So that first guess, the big point I'm trying to make is the first guess is really important. If there are multiple roots and you want a specific root, your first guess, even though that's pretty damn close to the actual root I want, it's going to end up getting some other root. Okay, that's enough then. So, let's come back to the specifics of the process. And then we'll do some examples in the calculator. Okay. Can you guys try to write down does anyone think they can write down Newton's method? The algorithm? You've obviously got it in your notes, but see if you can write it down from memory. Yeah, I'll start it off. What goes here? Anybody know? Exit. I like it. So it's kind of like, and then we're going to do shit to this. So it's my next better guess is going to be the first guess, or this guess, adjusted. Well, how do I adjust it? Minus? So I mean, that is where we arrived after doing what I said this was supposed to. We actually did it. We set up the general tangent line, we found the intercept of that, and then we solved for it. And that's what we got. That's where this came from. It came from doing exactly what I just said. I really want, because it's really, all right, when you see this, it's just a mix of shit, yes? But if I subtract this, isn't that delta x? If I multiply by f prime, isn't that m times x minus x1, right? You can see how this came from the equation of the line. Okay. So let's try, let's try a problem. So let's say I want to solve, what do you got, Jeff? All right, let's say, what do I have on this thing? I don't want to do the same thing. Okay, let's say I want to solve cosine x equals x cubed. Can you do a really rough sketch of this, and then on top of that, this? Do it. Do a rough sketch of cosine x, and then on top of that, do x cubed. You better give yourself a little bit of idea of scale. It doesn't have to be perfect, but you don't want to just do this. So it doesn't have to be perfect, but it has to be good enough so you can tell where they meet. And that's going to be max. And I'll tell you this, we'll go to positive root, right? Should be 2 roots here, I think. So if I graph cosine x, where does it go to 0? Yeah, by half, so like 1.57. What about x cubed? So at 0, x cubed is, maybe there will just be 1. Yeah. Let's just be sure. At 0, x cubed is, at 0,
X equals 0.
okay, there you go. At 1.57, let's say, here's 1, right? At 1, x cubed is 1, yes? And then it kind of connects, and at negative 1, x cubed is negative 1. So it kind of goes like this. Yes? So it looks like they intersect here. So this is 1. 1, 1, is that cool? So what would be a good first guess?
0.9.
0.9, I love it. So we can say x1 equals 0.9. So when I give you this problem on a test, everybody could have a different first guess, just based on how good your sketch was and so forth, and how much you remember what these things look like. That is how you get But good first guess. That's how. Now, if I'm you, on a test, I might just graph this and graph this in my calculator just to make sure, but you better show me this shit. Yes? And it better not be that great. It better be, I mean, look, is that great? No, that sucks. But it's good enough to get me my first guess. That's all I need. So agree with me? Okay. Now, what do I need to set up the algorithm? What do I need? There's a major thing I don't know yet. No, something even more fundamental than that. What is f of x? What does Newton's method do again? What does it find? What does Newton's method do? What's it trying to find? The roots, which is where the f of x equals what? 0. Take this and make it equal to 0. How do you do that? Don't put a 0 in, that's not what I'm saying. Try to get one side to be 0. So what's the easiest way to do that? Subtract cosine. So what's f of x? It's the thing that I'm trying to make 0, so what's f of x? What's f of x? X cubed minus cosine, this is f of x. Let me stop for a minute. You guys see that? Not every problem in the homework is going to be like this. Some of them will just give you f of x, which is nice. But if they tell you to solve an equation, you just pull one side to the other, that's your f of x, because that's what you're trying to make equal to 0. But I leave it like this to graph this, because cosine's easy, x cubed's easy, I can see my guess. Do you want to do a rough sketch of this? No, thank you. That's why I do it there. Now what do I need? Now I know f of x. Don't come at me with, right? I'm just looking at what this guy needs, yes? It needs a guess, it needs f as a guess, and it needs f prime. Okay, so what's f prime?
3x minus plus.
Well, that kicks ass. I love it. So, let's set up the second guess by hand, but then I want to show you in the calculator how to make the calculator do all the work for you, right? You just got to set it up. Okay. So our first guess is 0.9. So what is x2? 0.9 minus.
0.9 cubed.
Yeah, f of 0.9, so it'll be 0.9 cubed minus cosine of 0.9 divided by?
So 3 times 0.9 squared.
3 times 0.9 squared plus sine of 0.9. Stay with me now. Okay. And then you just gotta throw that shit in the calculator. Now, anytime you have a ratio like this, there are understood parentheses, yes? That's the top, that's the bottom. That's how you want to put it in the calculator. So go ahead and try to put it in your calculator, and I will catch up to you. Oh, I don't want to go over here. Point. Oh, what are you? Here. All right, you guys, well, it's all right, we'll do this one. 0.9 minus.
Should you put like another bracket around the whole then? Because now it's gonna take 9 minus that and then divide the whole thing by like.
Of course it won't. Order operations, what's the last thing it's gonna do? Subtract.
No, right, like that.
And then plus
.866, .866.
Yeah. So right now, I know my first guess is pretty damn good, because did that change by much? No. Right? I know we felt pretty good about the first guess, right? And then you would do it all over again. Now, do you see how quickly this gets annoying as shit? Wasn't it annoying just putting that first thing in? My name, parenthesis, oh, you got enough parenthesis, right? So, here is the best button on this damn calculator. You ready? Everybody do this. You ready? This is exciting. 0.9. No, Jeff.
No.
Enter. Ooh, look at that. Look at that. 0.9 equals 0.9. Good job, calculator. Right, do that. Do it. Do it. Seriously, do it. What am I doing that for? Because now there is a button in the calculator that has memorized 0.9. Which button is that?
Answer.
Answer button. And if I do something, what will the answer button have in it then? That
Answer.
new answer, yes?
Yeah.
So if I do what I just did, but I put answer instead of 0.9, then answer will have 0.866, blah, 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 blah. So then I can just hit enter because it's going to recalculate, but now instead of 0.9, it's going to put 0.86. Isn't that what I want to do next? Is put 0.86 in there? So what am I trying to say? So here's what I'm trying to say. So anywhere you see 0.9, anywhere you see xn, you're going to put ANS, which is right above your negative button at the bottom, right down here. So I'm going to put answer, minus, parentheses, answer cubed, minus, cosine, answer. And do you see why I put double parentheses there, right? Divided by 3 times answer squared plus sine answer. Right? You got everything? Yes. So if I hit it once, there's the 0.86. Now that's in the answer memory location. So if I hit enter again, it's going to put it in there for me. So if I hit enter, it's going to recalculate what it just did, but now what's it going to put here? This. Now, how much did that change by? Not a lot. It changed in the third decimal place, right? So x1 is 0.9. What's x2? Oh shit. x1 is 0.9. What's x2 up there?
0.88.
Yes. Well, point who?
866.
And what's this? This will be x3. Every time I hit enter, I get the next better guess. So hit enter one more time. Let's see. Did that change by much? It changed way down here. So if it said, bless you, if the answer correct to 4 decimal places, could I stop right now? What do you think? If I do it again, does it make sense it would only change like down here, if anywhere? So am I pretty good about the 8655 if I round? I know that's true up to that point, yes? If it said I want it true up to 8 decimal places, I might have to do it again, right? Let's do it one more time and see what happens. Jeff? Yeah, it stayed the same, look. Yeah. Now, it stayed the same there on the screen, but probably the 10th decimal place changed, and that's off the screen. Is that true, Jeff? 5, 10, no, maybe 12th decimal place. Yes?
So then, just to clarify, once you store the answer the first time in the calculator, you just keep pressing enter and it'll keep doing that.
Yeah, put your first guess in, hit enter, which seems kind of silly, but now ANS has that in it, so when you build the expression, you're just going to enter, 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 because every time it'll put that new number in. ANS has the last number that showed up on the screen. That's beautiful, right? I mean, that's the whole point of an algorithm, is to make it easily programmable, right? And that's why they use this algorithm to actually do it in the now, let's check this. Let's check this. Oh, what was the equation in the first place? I forgot. Oh, there it is. X cubed minus cosine x. All right, zoom 6. Let's take a look. There it is. So you guys remember, how do I find that root? How do I find the root? The root. I don't know if that's giving you trouble.
Second calc.
Okay, good. Second calc. Second trace, yeah, get a calc. So second trace, now I'm in calc. And I want to calculate the what? 0. And of course, now we know why this thing is saying left bound, right bound, because if my first guess sucks, it can adjust. So there's an adjusted Newton's method in here using the bounds to help it. That's what I wanted to ask TI for, and that's what they said. We're not going to give you that. So I got to give it a left bound, enter. I want to go to the right of the answer, enter. So now it's going to search between there, and then I want to give it a good first guess, enter. Now that looks familiar, right? So what I'm trying to tell you right now is, if I give you a Newton's method problem, you can always very easily check your answer. Yes? Insane. So, now again, this is a beautiful counter when a student tells me, well, my last teacher just let us do it in the calculator. No, the point of this is to go, humans told this stupid thing what to do. We didn't find it out on a beach somewhere after some aliens left it. So now you're at the level where we're starting to show you, how did we make this thing? There, that's how we made this thing. We threw that shit in there, and then we made the calculator. What can the calculator do really quickly? Calculations, holy shit. And what does it take to kind of get to a good place here? Do calculations. So it gets to the 100th guess in milliseconds, right? That's why I was able to do that almost instantaneously, yes?
Sometimes off of my calculator, I keep putting in the same thing, but the first time I got 1.1, and then it got different times errors.
So what happened is you put, oh, let's see.
If I did anything else, then I put a 6 times error.
Oh, you didn't, so you see how this you didn't have enough closed parentheses? You have 3 open, 1, 2 closed, another one open, another one closed, you need one more, closed. And that's the list of what's Was it the same thing on the bottom? I don't know, dude, I have to look at this. Alright, I have to look at it. Something, it's got, I know it's the parentheses, you got more parentheses than you need in there, which is making it hard to keep track of them. Okay, so, what I want you guys to do is I want you to do everything we just did, but do it for this. Let's see. Yeah, okay, I'm gonna get my 2 out. Now notice one little thing. Couldn't we have subtracted x cubed? And the whole process would still work. So your f of x could be different from somebody else, because you could I could subtract this, or I could move this over here, either way. The process doesn't give a shit, it's kind of the same to it. So do all the steps we did to solve this using Newton's. Oh, I'm sorry. Yeah, that's good. times, 3 times now. 3 times the point eight squared. Oh! I haven't even looked at it, and I never thought. Yeah, load radians.
What's the degrees?
I don't know. Oh. Well, I made that one easy. Alright, that's hilarious. I don't know.
Yeah.
Maybe it's a little more interesting. Yeah. I made shit up completely out of nowhere and that's too easy, so I'm sorry. How far along are you? I don't know. So let's make this a little more interesting, yes? Yes.
Did everything right.
So down one over one, down one over one, there we go.
Also, it's 3 minus x.
Yeah, when it was 3 minus 2x, it actually met right at 1, which is weird. I just made it up out of nowhere and I came up with a nice answer. You would be done then. Do you understand? Like, I don't need Newton. It's freaking 1. Next.
No.
Alright, so let's do this. So we see how 3 minus x, so 3 you're intercepting down 1 over 1, down 1 over 1. That's the easiest shit. Okay. So everybody might have a slightly different initial guess. Let's see.
Are we still using the method?
Yeah, yeah. did you guys go? What did you get for your F?
Root x plus x minus 3.
Okay. So you added the x, subtracted 3. Did anybody else just subtract the square root of x? Yeah? It's like more you did that, so I'm going to do it that way. So 3 minus x minus x to the 1/2. Might as well write it like that because, and then again, if you subtract the 3, add the x, you get your f of x that way. That's the Newton's method doesn't care. It's going to work either way. And now, of course, I have to do what with this?
The derivative of it.
Derivative.
A negative 1/2 x, right? No.
Huh? So that's 0, that's
Zero, one.
negative 1, and that's good.
Negative 1/2 x to the negative 1/2.
Now you see why Carmen and I would have went the other way, because then there would be less negatives. But this will work. Right?
Did you create the function and like you sketch the function, or did you get the same thing or how?
The problem is, all right, that's easy to graph, yes?
Yeah.
I barely have to think to do that. That's easy to graph. Again, I barely have to think to do that. Can you graph this easy? Without plugging shit in, right? Do you see what I'm saying? Okay. All right, now I can build my algorithm, yes? So I don't know. Somebody give me their x1.
1.8.
1.8. You could say 1.7, you could say 1.9, whatever, yes?
Wait, I'm still confused. Like, how do you find that?
So I graphed this, right? I keep getting emails, sorry. I graphed this, and I graphed this, and what does this equation says it wants to happen? It wants this to equal that. So where do they equal each other? About 1.8.
But how do you know?
That's 1, that's 2. Right? My scale, yes? So what is this roughly? Isn't it a little bit more than 1.5? Right?
Yeah.
But you could say 1.7.
Yeah.
Somebody else could say 1.9.
That's why, like, how are you supposed to know, like, exactly?
That's the problem. That's what I said. So
Okay.
everybody's x-wing could be a little different because if you graph this like a little different curve or something, we're not doing it beautifully perfect, are we? So this could look different. And look at my scale. Is my scale perfect? Shit, no. Right? So somebody else could have done a little bit different. They could have actually had graph paper. But as long as the first guess is decently close, the speed that it converges to the answer should be roughly the same. Especially, are either one of these functions really gross? What's a gross function? Here's a gross function. Oh, that's really gross. It's not even a function. But you get the idea. It says, going crazy in the shower. That's gross. That's gross. So then I want to really get my first guess close. Because if I'm trying to get this root and I'm just a little bit away, my tangent line could go, wow, and you can just, all right, stop. So what does this look like? So if I do, if I put 1.8 in, enter, then this is going to look like answer minus this, where I put an answer in place of all the x's, yes? Yes? Over -1 minus 1/2 answer to the -1/2. And then I can remind myself. You could even, if you don't like all the negatives happen, couldn't I kill that negative with these negatives, make that plus, make these positives? But I'm not going to, because I don't think you guys saw it. But you told it, of course you could. So let's see. Let's build this in here. Any questions on what I just did? Okay. So on your test, if you write that answer thing, that's the work. And then you just let the calculator, and then you just copy down the answer you get, right? Or I might ask you to list the first several guesses or whatever. So hit enter, write it down. Hit enter, write it down. Hit enter, write it down. All right? Okay, so let's see. I'm making notes. I can't see open it. Answer minus 3 minus answer. Ooh. Oh shit, did I do the answer yet? No. Let's start this originally. 1.8, that's the first step. Enter. Now I'm going. Okay. Answer minus. Answer minus. No, I'm sorry. 3 minus answer. Dadgummit. Trying to go by memory, it's never a good idea for me. Minus the square root of answer, right? Alright, stop. Is everybody with me so far? Or you can do answer the 1/2. Happy I didn't care. Divided by all this mess. What is it? -1, sorry. Yeah, -1 minus 1/2 times answer to the -1/2. Oh, that's exciting. Look at all those parentheses in there. Holy shit. Yes, yes, maybe, maybe. -1 minus 1/2 times answer to the -1/2. Parentheses on the outside, so the calculator knows that's the bottom. Right? We got eyeballs, it don't, so we gotta help it. All right, let's see what we do. All right, that looks pretty good. That's what I got for 1.8, right? So that's the second iteration, or second guess. Third guess, it's already starting to solidify, right? Fourth guess, it's there basically, right? Now it doesn't change at all. At least on the screen, right? Maybe it's changing in the 15th decimal place or the 20th decimal place. You guys semi with me? Now, what if, did somebody else have a different first guess? No, you all had 1.8?
No,
Really?
because like for me, like my sketches always is the best. I'll put up like 1.2 or something like that.
1.2? Okay,
Yeah.
let's see what happens. So if I do 1.2, and then I go back to this, I can redo the whole thing. Look at that. It's pretty, now here's a word. The method is robust if you have nice functions, or either one of these slopes going crazy, especially not the line slope, right? So you have the algorithm is robust, meaning strong. It can handle big deviations for functions that are nice, and a square root is stupid nice. It's just a parabola that fell over and lost its pants, right? So that's, if you want to look at that one. But let's see, what if I put in there 11? That's a really good first guess. Oh yeah. That's somebody really sketched a shitty graph. Let's see what it does. Look at that! Robust. What if I put 0.01? Oh, what am I doing? Yeah. All right, took it a little bit, but I got there, right? And again, it's because the functions are nice.
Just try a negative number.
Now, what's going to happen with a negative number?
Oh, square root.
Well, let's see. So let's put in there -1, right? And it's going to immediately go. Oh shit! It's going to immediately go. I don't know what I'm trying to do. This. Yeah. So again, you know, the domain of part of our function doesn't allow negatives. Yeah. So that's with me. A little bit. Okay. All right. And again, you got this handout that basically details the process for you. Yeah, so you can just follow this along. Oh.
Can I just try one of those?
Huh?
Can I just take one of those?
Yep.
I'll take a second.
What?
I'll take a second.
Okay. That's actually my last one. Bam. All right, so here's the deal. I am going to officially put 4.9 on the next test, so you are not responsible for 4.9 homework yet. Some of you may have already done it, which means you are ahead for the next series of stuff. 4.9 goes really well with chapter 5, so it's fine with me. Yes.
So what were the chapters that are covered on the test?
So remember, there'll be a related rates problem. So effectively it's 3.9 through 4.8. Right? And everybody got a practice test?
No.
Didn't I give this out? Anybody else need to practice? So I'll have an answer key for this on Monday. Our test is Wednesday. You don't have to worry about 4.9 homework yet, which is nice.
Real quickly, could you go over just like the similar triangle ratio thing?
Oh yeah. Let's do a concrete thing to show you why these ratios work. So if I had a little triangle just sitting here minding its own business, right? Pretend like it's the right triangle. Let's say it's 3, 4, 5. Yes? And then I double it in size. If I double it in size, how long is this side?
8.
8. How long is this side? 6. How long is this side?
Root of 8 becomes square root.
Or 10?
10. Technically, you're right, but double everything.
Are you trying to trigger
So-
their mouth and trigger
No.
that?
Yes, that's other aspects. So if I do small side to small side, of course it has, so I did this side to this side. That is 1/2. Why? Because that triangle side is 1/2. Aren't they all freaking 1/2? So any other ratio I make, this side to this side, of course it's still 1/2, because they're all half as big. Or I could do it this way, in which case they would all mean this big one is twice as big. So if I have you got me? Wait a minute. X 10 2 let's say 2 Y 5. This would be weird. It's too bad, Jim. Well, sure. What's one ratio you can create?
X over 10?
Yeah, X to 10. And then what's a ratio you can create where I know all the numbers?
No, 5 and 12.
Yeah, so you did small to big, so then small to big, yes? Couldn't you solve that for X? And then I could set up another ratio, small to big equal to this and solve for 1, yes? That's how similar triangles work. And again, they are based on the idea that if you blow a triangle up by a certain multiple, all the sides have become that multiple bigger. So of course their ratios will all be the same because they're all equally blown up. Is that? It's a very straightforward idea. You just barely use them, but similar triangles show up in a lot of calculus problems. Just to let you know. And we saw them actually back in related rates. There's at least one problem we did that involved similar triangles. So if you haven't done section 3.9 yet, the idea of similar triangles does show up at least once. Okay. That's enough. So next time I'll have the answer key for that practice test. Miguel's not. Miguel here? No. Okay. Have a good weekend, guys.